Watch the prediction. It's actually
So welcome back, everyone. So part 2, like part 1, is going to be about methods for articulating structure and data, articulating which inputs you view the most relevant. The difference is in part 1, we looked at really deterministic conditions, so these stability notions for clustering and the RIP condition for compressive sensing, whereas in part 2, we're going to be looking entirely at models that are probabilistic in some sense. So we're going to be using distributions over inputs in all of these models. So let me start with sort of 2 technical topics and then 2 kind of just lightweight topics at the end. So the first main thing I want to talk about are planted models and semi-random models. So let's begin with what's now a very famous problem, the planet Clique problem. There was a long time where planet Clique was like a pretty obscure corner of the universe, but we've heard a lot about it over the last 5 years. It's kind of gone viral. So what's the planet Clique problem? And so the idea is, what would be, in the spirit of having meaningful clusterings, could we have a distribution over clique instances where sort of there's a meaningful maximum clique to find? So you start with just, your basic random graph, Erdős-Rényi edge density 1/2. So that's this thing here. Then you plant a clique in it, meaning for some parameter k, you choose k vertices at random, and you just connect all of them to each other. So you add the clique, okay? And then the algorithm is given this as input. And of course, the algorithm is supposed to recover the clique in polynomial time. So this problem is only going to get easier as we take k bigger and bigger, right? The bigger the planted clique, the easier you're going to be able to find it. So you can ask questions like, okay, so how big do we have to take k before the clique problem becomes polynomial time solvable? Okay. So what's the state of the art? So the state of the art by Alon Krivilovich and Sudakov shows that, well, if the clique is at least a constant times root n, and here's the number of vertices, then there is a polynomial time algorithm that finds it. Okay? So that's an old positive result. These days we're hearing a lot more about the planted clique hardness conjecture, which is the conjecture that actually no polynomial time algorithm can recover cliques that are asymptotically smaller than this. So we don't know whether that's true or not. It's just sort of a hardness assumption one can put forth. And more now people are using the planet clique hardness assumptions to prove hardness for other types of problems. And also, lately we've been seeing some, really nice unconditional lower bounds for restricted models of computation, like sums of squares or like statistical query algorithms. But I don't want to talk about any of that stuff. Okay? This is a talk about algorithms, about upper bounds. I don't want to talk about lower bounds and hardness. So instead I want to say, okay, let's look at the algorithms for recovering planted cliques. Are they interesting? Well, the alone et al. Algorithm is interesting, actually. But what I want to convince you on the next slide is that if we're happy with just a tiny bit weaker guarantee, we could get it with an algorithm which is definitely not interesting. Okay? So let's say actually I made the clique a little bit bigger, so I made the problem a little bit easier. So square root of quantity n log n. That's how big the clique's going to be. I claim then you can recover it in polynomial time. Anyone have a guess what the algorithm might be? It's not a very interesting algorithm. Good. Just look at the degrees. Okay? So let me explain. So imagine what the graph looks like just when you have the Erdős-Rényi graph and you haven't planted the clique yet. Okay, edge density is 1/2, remember. So what's the degree of a vertex? Well, it's basically looks like a Gaussian with mean n/2. And, it's going to peter out, at plus minus square root log n standard deviation. The standard deviation is root n. So this is what the degree distribution looks like before you plant the clique. Now suppose you plant a clique of size at least, some constant times square root n log n. That means if you're one of these if you're one of the vertices that was selected to be in the clique, even if your degree before the planting was all the way over here, the clique will catapult you all the way to the right-hand side of the bell curve. Okay? So all of the clique vertices are going to be to the right of the bell curve, so you can just recover them by returning the top k, the vertices with the top k degrees. Okay, so, and I claim this is not an interesting algorithm in the sense that if you tried to run it on real networks, you'd get back the top k max degree vertices and they wouldn't be a clique and you would have missed out on the real clique. Okay, so this is not something which is going to generalize from this planet clique model to other models of networks. And the way I would describe this is somehow like in positing this one specific input distribution, it unfortunately kind of naturally led us to this algorithm which is sort of brittle and really kind of an artifact of the specific distribution that we assumed. And in general, we're going to aspire toward results that are more robust than that. Actually, just a quick step back. So Jay mentioned average case analysis in part 1. So that planted clique slide is pretty much the only slide of the talk that's on sort of basic average case analysis, by which I mean you really posit one known distribution over inputs and just optimize, say, expected algorithm performance over that input. Okay, so that's classical average case analysis. It's not to say this is not useful. Okay, there are definitely situations where average case analysis is exactly what you want to do. So if you have a problem, you have a very detailed understanding of the input distribution and it's relatively stable over time, and you don't actually need a general purpose solution to the problem, you just need to solve your one specific application. And increasingly, like in big data companies, actually all of these assumptions are met. So these really are real problems. So if you satisfy all of those things, then by all means, use the algorithm with the best performance with respect to the one distribution which you have good confidence in. But of course, if you're a little uncertain about the distribution or it's changing rapidly, or you want to have sort of more robust algorithms, then you really need to go beyond this. So that's the theme of part 2. What would be robust versions of average case analysis? All right, so let me show you the first version, which is going to be the idea of semi-random models. So the phrase semi-random actually comes from pseudo-randomness in the 80s, a paper of Santa and Umesh Vazirani. But the idea of applying to combinatorial problems was due to Blum and Spencer. And so they were looking at graph coloring problems. And the idea in a semi-random model is in addition to nature, i.e. in addition to an input distribution, you're going to have an adversary. And nature and the adversary will collaborate to produce an input which is then fed to an algorithm. And there's many ways you can define these models. We'll see several. So I'm going to look at the Feiga-Killian semi-random model for planted clique, where nature goes first, and what nature does is exactly the same as before. So nature, again, picks the Erdős-Rényi graph and plants a random clique. Then the adversary gets to go second and modify the graph. Okay? Now, if you think about it, we need to restrict the adversary, right? Otherwise, the adversary could just delete the original graph and replace it with a hard instance. So we're going to look at a monotone adversary, which is an adversary that can only affect the instance in a way that's intuitively helpful, that should make it easier to solve. So for the clique problem, that means the clique itself, it should leave alone. And the other stuff, the ambient stuff, if the adversary wants, it can make it sparser. It can delete edges that are outside the clique if it wants. Intuitively, this should just make the clique more pronounced and easier to recover. But if you think about it, that stupid algorithm from the planted model is not going to work. If you just take the top k degrees, in general, you will not recover this planted clique. The adversary can just delete lots of edges in between the clique and the rest of the graph, lowering the degrees of the clique vertices, and that algorithm is going to miss them. So it breaks that algorithm, which is good. So does it encourage us to design more robust algorithms for clique finding? It seems to. So the state of the art here, the threshold on k is actually exactly the same as in the planted model. So Feiga and Krautgeimer gave a polynomial time algorithm that recovers the clique even in the semi-random model, again for k down to omega of root n. Their algorithm is something that you might plausibly want to use or at least build on, which is a suitable SDP relaxation for the problem based on the Lovász theta function. Okay? So that's the state of the art for random and semi-random planted clique. I want to talk about one other semi-random model for a combinatorial problem, because this is somewhere, it both has a rich history and there's been some exciting developments just in the past few months, which I want to tell you about. So here it's going to be planted bisection. So this is a special case of what's called the stochastic block model. These days some people are calling this community detection, although if I'm honest, I think it's a little bit of a stretch to call it that. It is related, but I like to call it planted bisection. So you have two groups of n over 2 vertices. The bisection that you're planning is the bisection of the graph into A and to B. Okay? And you want this bisection to be cheap, meaning that fewer edges cross this cut than any other bisection. So in the random model, so again, this is not the semi-random model, this is just the random model, you're going to fill in the two groups with a relatively large edge density, P, and then you're going to fill in the edges in between A and B with a relatively small edge density, Q. So Q is going to be less than P here. Okay? So each edge here is there independently with probability P. Each edge here is there independently with probability Q. And here intuitively, the bigger the gap is between P and Q, the more obvious will be this planted bisection. The more obvious will be this grouping of the graph into A and B. So what people have thought a lot about, and actually there's some pretty deep and kind of amazing work on this, is for exactly which values of P and Q, so for how big a gap, can you recover this planted bisection in polynomial time? And there are very precise answers known to this question, and you even have things in the semi-random model. So what would be the natural monotone adversary for bisection? Well, again, you should make the problem only easier, the adversary. So it's allowed to add edges within each of the two groups, or it's allowed to delete edges between the two groups. So that's the semi-random model of planar bisection, and the results for the random model generally extend to the semi-random model. And actually, so this is kind of like the limits of my animation ability. So let's just like watch that a couple times. Before the adversary, after the adversary, before, after. Yeah. Okay. So the state of the art for the planar bisection was basically the same, random or semi-random. You had to work harder in the semi-random model, like in planar Clique. But now, actually, for a variant of the model, we have the first separation, really showing that semi-random models are a strictly harder problem. So for this, we need to look at the sparse regime. So again, remember, P is the edge density inside the groups. Q is in between the groups. We're going to think of both of these as being really small. Okay, so like constant over n. Okay, so they're going to be different constants, and A here will be bigger than B, because P needs to be bigger than Q. And you think about this for a second, you realize you're not going to recover A and B. No way. These edge densities are so low that in our Erdős-Rényi graph with these kinds of densities, you don't even have a connected graph. You have isolated nodes. You have a giant component, but you have a bunch of isolated nodes. How do you know if an isolated node is supposed to be an A or an B? You have no clue. Okay? You have no information at all. So you could still hope to do partial recovery, though. You'd like to at least classify the vertices into A and B better than random guessing. So again, you can ask the question, for what values of P and Q can this be done or not be done? Beat random guessing as far as classifying into A and B. So again, in the random model, in a sequence of pretty deep results just a few years ago, this question's been totally nailed, right? And it's kind of an amazing criterion. So remember, A and B are the coefficients in the edge densities, and so we expect that the bigger the gap is, the bigger A minus B, the more possible it should be to do partial recovery. And in fact, if and only if A minus B quantity squared is bigger than 2 times A plus B, in that case, you can do partial recovery even efficiently. If that condition is not satisfied, you cannot do partial recovery even information theoretically. Okay? So you kind of completely nailed down the regime, the parameters in which you can do this. That's for the random model. So what about for the semi-random model? This is defined just like before. So an adversary can delete edges crossing the bisection or add edges inside each of the two clusters. And so this was just in stock a couple months ago, Moitra, Perry, and Wine. They show there's actually a separation. They show that in the sparse regime, there exists a monotone adversary that can actually screw up every algorithm, even in parameter regimes where this condition holds. Okay? So there exists an infinite set of choices for A and B, so that this condition holds, and hence partial recovery is possible in the random model, but it is not possible in the semi-random model. There is a monotone adversary that can screw up all of the algorithms. The gap isn't huge, so if you replace this with a larger constant, all of a sudden you can get semi-random algorithms for recovery, but this shows there really is a difference between the two models. Okay. So there's still nice open questions, I think, around semi-random models. I think there's still a lot to do. So, one thing that sort of you can't help but notice is for all of the positive results for these semi-random models, it seems to always be a semi-definite programming relaxation, which kind of gives you what you want. And there's a question of, is there some generic sense in which SDP relaxations are the best robust algorithms, the best algorithms for semi-random models? There's some suggestive results along these lines in the Moitra et al. Paper that I mentioned. You can imagine trying to weaken the assumptions about nature and or about the adversary, right? So maybe nature doesn't do independent edge probabilities. Maybe the adversary can at least have some violations of monotonicity. That's important, having weaker models and positive results. There's some nice results, again, by Makarichev and Vijayaraghavan. These are different papers than the multi-way cut one I mentioned before. Those are for graph partitioning problems. And what else? So the Moitra et al. Separation between the random and the semi-random cases, that's information theoretic. You could imagine cases where you'd see a computational separation between the two regimes, where information theoretically you can recover up to a certain threshold in both the random and the semi-random cases, but you can only get it to be computationally efficient in the random case. at least based on some average case assumptions. And then finally, like I said, it's sort of a cottage industry now to prove, conjectured average case hardness or worst case hardness for problems, using planted clique. It's only a weaker assumption to assume that it's hard to do semi-random planted clique, right? It's a harder problem, so it's a weaker hardness assumption. So, how many of the implications of planted clique hardness extend under the weaker semi-random hardness assumptions? Another thing I'm curious about. While I'm on the topic of open questions, I can't help but briefly plug a recent paper I wrote with Gloverson, Sontag, and Yildirim. So this appeared in a machine learning conference because there's connections to structured prediction. So I think this sort of flew under the radar of the algorithms community, but there's some really juicy open questions here I think people in this room and in the algorithms community would really like. So let me just show you what those open questions are. So what's the model? So again, there's going to be some unknown object, some planted object that we want to recover, at least partially. So what you do know up front is a graph, okay? Maybe like the grid. Maybe you're looking at an image and each pixel corresponds to a vertex. What you don't know is an unknown binary labeling of the vertices of this graph. So that's the red and the blue of the different vertices. So imagine I gave you the graph and I didn't give you the colors and I wanted you to tell me what the colors were. All right, so what information do I give you to try to make inference about who's colored what? Well, suppose I give you the parity of each edge. Okay, so like this edge, it has different endpoints, so the parity would be 1. This edge has the same color endpoints, so its parity would be 0. 0, 1, 1, 1, etc. Suppose I gave you a parity for every edge. Actually, not quite. So that would actually be easy if you think about it a little bit. You can just immediately recover up to a permutation of red and blue, the unknown labeling. So it's interesting when the parities are noisy. Okay? So I give you what I gave you before, except with some probability p, each edge gets flipped. Okay? So maybe you get a 0 here if it's a noisy edge. Maybe you get a 1 here if it's a noisy edge. Okay? So that's the model. The noise can be random or semi-random. It doesn't matter for our results. And the goal is to recover x, to figure out which nodes are red and which nodes are blue. Actually, one thing, again, sort of like in that sparse regime for planted bisection, you realize immediately that if the graph is too sparse, you're not going to be able to figure out all of x. Right? So like in a bounded degree graph like the grid, some of these vertices will just have all corrupted edges around it, and you're going to have no way of figuring out where that vertex belongs. Okay? So at least in general, we're thinking about approximate recovery, where the classification error, the number of nodes, the fraction of nodes that you get wrong, should be going to 0 as the noise goes to 0. Again, when the noise actually is 0, we know you can do recovery, and you'd like to say that with small noise, you can recover almost as well as in the full information case. Okay. So what we prove is we basically show you can do this in some graphs and you can't do it in some other graphs. So for example, if the graph's an expander, we can show that you can always approximately recover the unknown binary labeling. That's not computationally efficient, unfortunately, our algorithm. On the other hand, for planar graphs, specifically bounded phase planar graphs, including the grid, which is what we were motivated by, you can do approximate recovery, and even computationally efficiently. Okay, so as the noise goes to 0, there exists an algorithm, even polynomial time for the grid case, so that the classification error goes to 0 with the noise. On the other hand, these are not trivial results. And in particular, you have to use the graph structure when you prove these results, because some graphs it's just false. If I give you a path graph, actually, even as I take the noise to 0, every algorithm is going to have classification error remaining bounded away from 0. The error does not go away in the limit as you take p to 0. Okay? So those are sort of the highlights of our results. We have some cases where we know how to figure out what x is. We have some cases where we can prove you can't. And there's so much stuff we don't understand. It's a little embarrassing, actually. So I'd love to have a characterization, or at least a weaker sufficient condition, on the graph structure, which is sufficient to get approximate recovery of this unknown labeling. It seems like some, expansion is too strong, right? The grid isn't an expander, but we can still do it. But maybe some weaker analog of expansion is what's sort of driving these results. There's cases where we need polynomial time algorithms and we don't have them. A natural way to modify the model is to get noise, signals not just from the edges, but also from the nodes. So maybe for each node, I tell you red or blue, and 3 out of 4 times it's right, 1 out of 4 times it's wrong for a node. We have no algorithms which take advantage of extra noisy, of additional noisy node labels. And finally, so two labels is great if you're just trying to like segment an image into the foreground and the background. But usually in image segmentation, you kind of have more than one regions you want to segment stuff into. That would correspond to a labeling which is not binary, which has more than just two possible colors. We have literally no results even for 3 colors. We don't even know where to get started. Okay, so lots of opportunities here, I think. Yeah.
How it is related to solving linear equations with errors? I mean, they are hard because it's like linear equations. Here it's only pairs, but there are hardness result and
Parities. Yeah, for like learning noisy parities, you're saying.
Solving linear equations with errors. I mean, this is what you have here. No?
Sure. Yeah, there's no formal connection known. I mean, I see the analogy, but there's no reductions known between the problems.
If it's parity for each edge, I mean, it's like unique games, right? It's noisy unique games, 2 labels.
Every set of equations translate to a graph, right?
Okay. So the claim is this is a special case of other known hard problems, or?
Yeah.
Okay. So you hope to?
For the worst case graph, like you should get the hardness.
Well, I also want to point out you're talking all about computationally efficient results. I'm also interested just in information theoretically, like when actually can you recover this labeling and when can you not, in the spirit of the results we talked about in the planted models. So I agree. For the computational results, when you're in the regime where it is information theoretically possible, maybe that's the right avenue for actually proving hardness, that you're not going to get computational results matching the information theoretic ones. But even the information theoretic side, we really don't know. So, okay.
What's the meaning of the bounded phase condition of paragraphs for which to have a complete result? Means the bounded number of phases?
No, sorry. Bounded number of edges per face. So the dual graph should be bounded degree. Yeah, thanks. Yep.
So you would have phase transitions over here, like for the previous setting, where you have like this condition where recovery is possible, and as soon as the error crosses it, it's not possible. So here it seems like it's
a smooth. That's right. That's right. I mean, in part because our objective function here isn't binary. I mean, you could imagine, and maybe people have done this, but you could imagine looking at partial recovery and graph bisection and talking about what fraction of the nodes do you get back correctly as a function of the parameter values. So that would be the analog of the kind of question we're asking here. Yep.
So I think computationally, given that the absolute fraction of the edges are flipped, what we can do is we can recover some labeling, which satisfies 1 minus root the absolute fraction of the labels. But I don't know whether that's going to be consistent with that.
I think it's more that it satisfies 1 minus root epsilon fraction of the constraints. Yes. Yeah. But that's not our objective function, right? And this is a difference from the CSP formulations of this. We don't care about how many of these things. Right, so we know they're noisy, so we really don't care how many you conform to. We care about how many vertices you got right. So the technical work here is largely saying, okay, well, what if we do some optimization based on the edges? Under what conditions can we translate that to a bound on the nodes? That is sort of the nature of these proofs. Yep.
Is there any specific algorithm or result that you use for 1G as a path, or the approximation ratio?
So no, the path is a disaster. The path, you basically just lose too much information. Just you'll have a couple edges get flipped, and because there's sort of only one path in between any 2 vertices, you just completely lose any information about how things are correlated with each other. So the lower bound for the path is information theoretic. It's not about algorithms. It's just you don't have enough information to do it. All right, so that's the first main topic I wanted to do. This is sort of one other technical topic I wanted to cover, and then we'll have 2 short topics at the end. So next is going to be smooth analysis. So this is another type of a semi-random model where nature and the adversary can collaborate. And so this specific semi-random model was proposed by Spielman and Tang. The order in which the 2 players go is reversed. So here the adversary is going to go first. And for some computational problem that you fixed, the adversary will pick some input. Think of it as like a hard input of this computational problem. Then nature is going to add a small perturbation to this input chosen by the adversary. So it just flicks it a little bit intuitively. And what do you want? You want an algorithm which, no matter what the adversary does, the algorithm should do well on average over nature's perturbation. Okay, that's the goal. And still, kind of the biggest killer application of smooth analysis is arguably the original one by Spielman and Tang. So they were thinking about linear programming. And specifically, they were thinking about the simplex method and the running time in a smooth sense of the simplex method. And so let me tell you about the perturbation model for linear programs, right? So linear programs specified by the objective function, the constraint matrix on the right-hand side. So they proposed that an independent small Gaussian gets added to each entry of the constraint matrix and each entry of the right-hand side. Okay? And small here, that's controlled by, say, the standard deviation of this Gaussian, which is what I'm using denoting by phi. Okay? So that's the model, and they show that in this model, no matter what linear program you start with, on average over this perturbation, the expected running time of the simplex method, at least if you use this one pivot rule, the shadow pivot rule, is polynomial. So what does polynomial smooth complexity mean? Well, it means, first of all, it should be polynomial time in the input size, like usual. You're also allowed polynomial dependence on 1 over the size of nature's perturbations. And if you think about it, some dependence here is clearly needed, right? So as the perturbation goes to 0, we know that the running time of the simplex method blows up to exponential. So it needs to be for sufficiently big perturbations. So what this is sort of saying is, as long as the perturbations are at least inverse polynomial, then this will run in polynomial time. Okay? So that's the result for the simplex method. I'm not going to say really anything more about this, both because I think this result is well known, and I want to focus on some less well known ones. Also, it's a quite technical result, so it's kind of hard to peek under the hood in limited time. So the next thing I want to mention is a really nice result of Bayer and Waking in the context of binary optimization problems. So let me tell you what the goal, what are they trying to do? They're trying to understand, okay, so Spielman and Tang, they used smooth analysis to analyze a specific algorithm. They were motivated by the specific case of the simplex method, and they wanted to know what was its performance. Bayer and Waking are motivated more by problems than by algorithms. So they're asking the question, for which problems does there exist some algorithm that has polynomial smooth complexity? And they wanted to understand which problems have polynomial smooth complexity and which ones do not. Okay? So Spielman and Tang sort of took the algorithm as fixed up front. Bayer and Waking are happy to design a new algorithm to certify that your smooth polynomial time solvable. Okay, so what is a binary optimization problem? So this is the family of problems in which they get a very clean characterization. So maybe think of knapsack as the canonical binary optimization problem. So in general, you have n binary decision variables, like whether to put an item in the knapsack or not. Let's assume that the objective is to maximize the total value subject to feasibility constraints. And the perturbation is going to be here in the coefficients of the objective function. Okay, so the VIs, again, you can think of as sort of lying randomly in some interval of at least inverse poly length. And then the other thing you need to specify is what are the constraints. And as you vary the constraints, you get different problems with wildly different complexities. Okay, so obviously knapsack is one. That just says the feasible sets are the collections of items whose weights are at most the knapsack capacity. You could have polynomial time solvable algorithms like maximum spanning tree, or you could have like super hard problems like max weight independent set. Those are all special cases of binary optimization problems, just depending on how you set the constraints. So Bayer and Waking give an if and only if characterization for which binary optimization problems have polynomial smooth complexity, i.e. admit an algorithm with smooth polynomial running time. What is the characterization? A binary optimization problem is in smooth polynomial time if and only if it can be solved in pseudo-polynomial time. So for example, if you have a weakly NP-hard problem like the knapsack problem, it actually becomes easy once you path to the smooth model. You can solve it in polynomial time, smooth polynomial time. If you have a strongly NP-hard problem, it does not become easy. It remains hard even in the smooth model. Okay? So that's the result, if and only if. So let me say a little bit about the proof. This will be the one thing I say a little bit about the proof in part 2, in particular because there's a nice connection to a famous result called the isolation lemma. So I'm only going to talk about the if direction. The only if direction is easy. That would just say, if I promise you that you can solve something quickly under perturbations, then you could solve it in pseudo-polynomial time. And that you just prove by taking a suitably small random perturbation. So what about if, so the hard part is to say, suppose the only thing you know about this binary optimization problem is that I give you a black box that solves it optimally in pseudo-polynomial time. That is all you know. And you have to prove that there's perhaps some other algorithm which runs in the smooth sense in polynomial time for randomly perturbed VIs. Again, think of the VIs as lying, say, uniformly in some interval of inverse polynomial length. So think of this as polynomial. Okay? All right, so the way this is done is through the isolation lemma. This was originally proved by Momoli, Vazirani, and Vazirani in the context of parallel computation, but it has lots of applications across theoretical computer science now. So let me tell you what the original version of the isolation lemma was. They were thinking about matchings, but the proof works for any binary optimization problem. And they said, suppose you have a graph, an unweighted graph, and now suppose you independently assign a random integer to each edge of the graph, say between 1 and n squared, or something like that, okay? Then, with high probability, there will be only one. There will be a unique maximum weight matching. There will not be two different matchings that are both maximum. Okay? So that's the isolation lemma. With high probability, over the choice of the integers for the edges, there's a unique maximum matching. Or the way I want you to think about this, by saying it's a unique maximum matching, they're saying that the gap between the best matching and the second best matching is at least 1. Okay? They're arguing a lower bound on the gap between the first best and the second best. So in the present context, we're not dealing with random integers, we're dealing with these perturbed VIs, but that just kind of scales this whole argument down by a polynomial factor. So now, really using the isolation lemma out of a box, you can show that once you perturb the coefficients of the objective function, with high probability you have a gap of at least inverse polynomial between the first best and the second best solutions. Okay? So there's a non-trivial gap between the first best and the second best. How does that help us? Well, now we can just sort of, in a lazy way, use our assumed pseudo-polynomial time algorithm. We'll only read as many bits of the VIs as are necessary so that we're sure we've actually distinguished the first best from the second best. Since they're inverse poly apart, we only need a logarithmic number of bits to do this. You feed that into the pseudo-polynomial time algorithm, it's actually going to run in polynomial time, and we're done.
You don't have issue with rounding? I mean,
With
the rounding, I mean, you will read the amount of bits, but you don't know if to round up or to round down.
Yeah, so you do need a lemma here, but there's something very clever where basically you run the pseudo-polynomial time algorithm not just sort of like for the current set of VIs, but also kind of for the worst case setting of what the rest of the bits could possibly look like, which again just corresponds to adding 1 bit. So you really run the pseudo-polynomial time algorithm twice. You know, once with the current set of bits, one with kind of the worst thing it could be for your optimal solution, and you check that you get the same thing. And if you get the same thing both times you run the pseudo-polynomial time algorithm, then actually you know, guaranteed, you've identified the optimal one. So you're right, you need to certify it, but that uses the same ideas. Good question. Other questions? So the last thing I want to say about smooth analysis is to just highlight where I think there's the biggest opportunity for really high impact work. I think work that would be really important. And this concerns local search. Simplex method, we mentioned at the outset, there's this embarrassing gap between the worst case running time and the empirical running time on almost all instances. The same thing is true for local search problems. And to be clear, when I talk about local search, I'm not talking about the quality of the local optimum that you reach. It might suck, okay? That's not my problem. What I want to focus on is the number of iterations needed until you reach some possibly bad local optimum. And that, basically, even though it's almost impossible to find an instance where a local search algorithm, runs sort of much slower than linear, nevertheless, theoretically, one can contrive worst case examples for most local search algorithms where they do require an exponential number of steps to reach a local optimum. So again, just like with the simplex method, with local search, we have this exact same gap of exponential worst case running time with, often linear or better running time in practice. So again, this would seem to be right in the wheelhouse of smooth analysis. Seems like there should be great applications here, and actually there are. So there's already been some really nice works in this area. So, for example, one I like is on k-means, which is one of the most widely used local search algorithms. And so Arthur, Vasilevsky, Manthe, and Roglin, they proved on the one hand the worst case running time is exponential. It's actually not that easy to prove, but they proved that. And then also, in a smooth sense, if you perturb the points that it's clustering, then it does have smooth polynomial running time. So I don't, that result's a little more technical, so I don't want to talk about it too much. But so let me talk about an easy result to give you kind of the flavor of this topic, of smooth analysis of local search. So let me talk about the traveling salesman problem, okay? So there's a bunch of different local search algorithms you can define for the traveling salesman problem. I want to talk about the 2-opt heuristic. So let me remind you what the 2-hop heuristic is, right? So at any given time, we have a TSP tour we need to define, which tours could we move to in one step? What are the neighboring tours? So here's what you're allowed to do in 2-opt. You take your current tour, you pick any 2 edges that you want of the current tour, you remove them. That shatters the tour into 2 different pieces, 2 connected components. And then you reconnect those 4 vertices in the unique way that gives you another connected graph. Okay? So that just moves you from a tour like this to a tour like this, or vice versa. Okay? So that's the 2-hop heuristic. Choose your favorite pair of edges and do this swap. Okay. So Englert, Roglin, and Vauquin analyzed this 2-hop heuristic, and actually they work hard to prove some really good running time bounds, smooth running time bounds of the 2-hop heuristic. I just want to show you that if we're willing to be sloppy with the polynomial time bound, if we're willing to have kind of a bad polynomial bound, we could do this very easily. Okay? So what's the idea? So the idea is basically to just combine the isolation lemma with the union bound. All right? So let me say more. All right, so what's a method by which you could prove that local search is going to run quickly? Well, a sufficient condition would be, suppose it makes a lot of progress at every single time step. Right, so suppose every improving local move you ever take, you decrease the distance to the best solution by some inverse Pauli factor. That means you're going to stop, if nowhere else, at the global optimum within a polynomial number of time steps. So that's exactly how this is proved. You prove that actually every single improving local move you might ever see will, with high probability, improve by a lot. Okay? So that you can only have a polynomial number of time steps before terminating. So how do you prove that? Well, what's special about 2-opt is there just really aren't that many different local moves that ever come up. Right? So yeah, you have a lot of tours and stuff, but any move from one tour to another really just involves a quartet of vertices. So there's really only n choose 4 local moves, okay? A polynomial number of local moves. Now, if you just fix one local move, and you want to say this one local move, if it's improving, improves by a lot, then you just use the isolation lemma argument from the last slide. It just works out of the box. So for a fixed local move, you know that with high probability, it's going to be big. If there's only a polynomial number of local moves, union bound tells you that every single local move will make a big improvement, and so therefore you can't run too long. You run in polynomial time.
Does this generalize to k-opt moves?
Yeah, with an exponential dependence on k, sure. There's going to be, right, so you're going to have like a 2k up here kind of thing. Yeah. I don't know that there are any results known which would be poly in k and n. I'm not sure if Englert et al. Proved that or not. I don't remember seeing a result that was poly in both k and n. That'd be nice. Okay. All right. So this same trick of just taking a union bound over all possible local moves can be used in other problems. So this is, again, this is kind of like the easy case. This is when, smooth analysis just kind of immediately gets you what you want. Think, for example, about max cut. Okay? And I have in mind the flip neighborhood. Okay? So in any iteration, you take one vertex from one of the 2 sides and you move it to the other side. Okay? So that's the local search algorithm we're talking about. If the graph that you're doing this on has bounded degree, or degree up to log n, again, it's pretty easy to prove that there's only a polynomial number of different local moves that ever come up. So again, by the isolation lemma and the union bound, you can just prove that all of them make healthy progress, and therefore you're just not going to take that many steps. But what about in a general graph? So in a general graph, there are an exponential number of sort of fundamentally distinct local moves you might take, and we don't know. We actually do not know the smooth running time of local search and max cut with a flip neighborhood in a general graph. We do know, and this is a non-trivial result by Escheid and Roglin, that at least it's not worse than quasi-polynomial, meaning n to the log n. Okay? So that's an upper bound on the smooth complexity of local search for max cut. We do not know if it's polynomial or not. It's suggestive that it's polynomial, but no one knows a proof.
I don't understand. So isn't the local move just moving a vertex from one side to the other?
Yep.
So why do you ever have more than, you're saying?
Because, so with respect to a given configuration, so if I fix the current cut, you're absolutely right that there's only n different moves. But then, this cut's going to be changing. So you have an exponential number of different cuts.
You're talking about the whole history, right?
Whole history, okay. Yeah. And that's what you need for this union bound. You really have to say everything that ever happens, I don't want to understand it. I just want to know any local move you ever take is going to have healthy progress. Yep. Good. Other questions?
This is weighted max cut, or?
Yes, you're right. I should have said that. It's weighted max cut. Say like real numbers between 0 and 1. Yeah. In fact, I mean, this is even open just in the average case analysis world, I think, where you have a uniform 0-1 number attached to each edge. I think even that is not known. Yeah.
So do all the analysis proceed in, I mean, is there any other form of analysis, or do all the analysis proceed by isolation, lemma, and including?
No. So I'm sorry if I gave that impression. So I focused on the easy ones just because it's a tutorial. So for k-means, you have to work a lot harder, and still on some level, you're taking some kind of union bound at the end of the day, but you have to be very clever about sort of equivalence classes of different moves, and then you take a union bound over a polynomial number of equivalence classes. And here again, there is, sort of a union bound, but they somehow have to again say, kind of have these equivalence classes of sequences that might come up to union bound over. So it's not, I mean, it's quite non-trivial to get quasi-polynomial, to get sub-exponential. That requires work as far as we understand. Okay. All right, so there's an obvious open question. Specific case of max cut with a flip neighborhood, is a polynomial or not? I would definitely like to know the answer to that. Actually, I wonder if something like much more sweeping is true, right? So if you think about that Bayer-Vocking result, that said, whenever you're solvable in pseudo-polynomial time, then you're also solvable in smooth polynomial time. Local search problems, they're all solvable in pseudo-polynomial time. This is sort of what Sesh was alluding to, right? So say you have integer objective function coefficients, every single step you take is going to improve by an integer value. So if you have poly-bounded coefficients, it's only going to run for a polynomial number of iterations. So the hypothesis in the Bayer-Vocking result actually holds for every local search problem pretty much. But this is about sort of finding a local optimum, not about finding a global optimum. And so we don't know if this is true. But I could imagine that for pretty much any binary optimization problem and any way of defining the neighborhood structure so that you have polynomial diameter between any two feasible solutions, for all I know, every single problem of that form has smooth polynomial complexity. I could imagine that being true. And this has been driving me crazy for years, I have to say. So if you have ideas, I'd love to hear them. Again, the issue is sort of avoiding the union bound, right? So the naive union bound is not going to prove this. In general, you have an exponential number of fundamentally distinct local moves. You have an exponential number of local optima. It's kind of hard to figure out how to handle them.
So what do you mean by polynomial complexity? That polynomial time to get to a local optimum?
Yes.
Or is it you get to a global optimum?
No, to a local optimum, yeah. Okay, and then I should say that even in the simplex method, which maybe you think of as being resolved for 15 years, there's actually some really important open questions that would make that theory kind of more immediately meaningful to kind of what we see in practice. So for example, we know nothing about non-Gaussian perturbations. We know nothing about the most popular choices of the pivot rule. We only know it for the shadow pivot rule, which is kind of, the easiest one to prove things about. And then another important one would be sparsity preserving perturbations. So remember, when we talked about the Spielmann-Teng model, we talked about how you add a Gaussian, a small Gaussian, to every entry of the constraint matrix, every entry of the right-hand side. Lots of the linear programs we care about have sparse constraint matrices, and the algorithms that solve them really leverage that sparsity to do well. So could you get away with only adding a small Gaussian to the non-zero entries of a constraint matrix? That would be really a quite major result if someone could prove that. Okay, so questions? That's the smooth analysis section. 2 more topics, but both are pretty short. Yeah.
Analogous to the sparse question, in these maximization problems, what if just you didn't add Gaussian noise to every coefficient VI, but to some random subset? Do you know anything, sort of a large enough random subset? Do you know anything there? Or?
I'm trying to think if the proof gives you something. I think you'd have to talk about I don't know that you could have something generic for every binary optimization problem without perturbing everything, but for specific binary optimization problems, I think you could get away with a weaker assumption. Yeah, but I haven't seen any results on that, so it's a good question.
I guess it's not known if you multiply by random noise instead of, because then zeros will remain zeros.
That's right. That's right. I think there's some, I feel like there's some partial results that I saw once, but it's basically open. Yeah. Yeah.
Is it possible to compare the hardness of programs by their distribution? I mean, like, although they are all NP-hard or they are all binomial type problems, but probably some, can you caricature the fine-grained complexity using the distribution?
I don't understand what you mean by using a distribution. Are you asking about average case hardness, or?
Yeah, because for example, next you will describe the benchmark for algorithm, right? Based on some distribution. But how about the problem itself? Although each problem probably has some specific distribution that can be easier to solve, but how do you compare two problems? The hardware
with different distributions. Yeah, I mean, so I think you're touching on sort of a really important issue that unfortunately we have not that much theory about. So Luca Trevisan here at Berkeley is one of the experts on this. So on average case complexity, like we just don't have we don't have a lot of reductions between different problem distribution pairs to other ones. So that's been a wide open question in complexity theory forever, basically. And people, there's been some nice progress, and I think we should keep working on it. But that average case hardness theory is not mature enough to connect to many of the things I'm talking about today. I think someday it will be, but we're a long ways from that. Okay. All right. So I want to say a little bit about other types of what I call hybrid models. And so what I mean by a hybrid model is some kind of interpolation between worst case and average case analysis. And the thesis, which I've given you examples for, and I'll give you more examples, is that for lots of problems where worst case analysis fails, the right thing to do is sort of a robust version of average case analysis, one of these hybrid models. So what do I mean by this? I just mean that so in average case analysis, I tell you one distribution, and you optimize for that one distribution. In a hybrid model, I give you a set of distributions. I say, look, I promise you I'm going to pick one of these distributions and draw an input randomly from it, but you don't know which distribution it's going to be. Okay? And you want to have an algorithm which does well simultaneously for any distribution that I might choose, okay, for every distribution that you might encounter. That's what I mean by a hybrid model. So worst case over the choice of the distribution, average case with respect to that worst case distribution. Okay? Let me point out that the last two topics are special cases of these hybrid models. So to tell you how it's a hybrid model, I just have to tell you the distributions. So think about like planet Clique, for example. Right? So we have this initial input distribution, which is just nature, the Erdős-Rényi graph of the planet Clique. And then we have this monotone adversary. And the monotone adversary just maps each possible output of nature to another graph. So if you combine a monotone adversary with nature, you get an induced distribution over graphs. As you vary overall monotone adversaries, you vary overall distributions you have to handle in the semi-random planet Clique model. So there we were exactly asking for an algorithm which does well, i.e. is correct, simultaneously with respect to any instance in this class. Similarly, in smooth analysis, now you have one distribution for each point that the adversary might choose, so for each input. And for that input, you then look at the perturbation around that input. You want an algorithm that does simultaneously well for every one of these sort of perturbed point masses. Let me mention some other examples which we either have seen earlier in the week or will see tomorrow. So Matt talked a lot about secretary problems, more generally, random order problems. So, in the secretary problem, an adversary, if you like, thinks of n different numbers, whatever it wants. But then nature comes in and presents them to the algorithm in random order. Okay, so again, you kind of want an algorithm which does well, no matter what the adversary does for a random ordering. That's, again, a hybrid model. In Adam and Nikhil's talk on Tuesday, we saw some statements of the form that some natural algorithm, prior free algorithm, is simultaneously competitive for any MG1 system. And the point here is that this G, this is the service time distribution, they were getting competitive guarantees no matter what G is. So that's, again, a family of distributions as you range over possible Gs, and a single algorithm that's competitive with optimal for all of them. And then Anna, I hope you go to her talk tomorrow morning. One of the things she'll talk about is prior independent auction. So this is part of algorithmic game theory, where, again, you don't assume that you know a distribution like you historically do in economics. You just assume something like independence of different bidders, and you want an auction which does almost as well as optimal no matter what the distribution actually is. Let me just mention again, like I said, the paging literature, sort of anticipates much of what's been going on this century, and so they also had notions of different hybrid models. This is the paper I mentioned at the beginning, Koutsoupis and Papademetriou, called Beyond Competitive Analysis, that gave rise to the title of this tutorial. If you went to Ellie's nice talk yesterday morning about learning, you might be wondering about that. That may seem to you sort of like the OG hybrid model, right? So back in the 70s and 80s. How is it a hybrid model? Well, again, there's an unknown distribution. Okay, I promise I'll give you IID samples, right? So you know something about the samples, you know their ID. but you don't know the distribution that they're IID from. And you want a single learning algorithm which works well simultaneously whatever the unknown distribution is. Works well in that context means low classification error. Okay, so you classify things almost as well as the target concept or the best concept in your class. So this, but this is historically about classification, this PAC learning model. And so you might wonder, we've seen all these hybrid models that are about sort of designing algorithms, choosing algorithms. Is there some way to, get the PAC learning sort of, philosophy in the same room as the algorithm design philosophy? And so I want to briefly just sort of point out that there's been a lot of work along these lines just very recently. This is kind of, which I'm very excited about. So the first example of sort of taking a learning theoretic approach to algorithm design with worst case, with sort of performance guarantees is the literature on self-improving algorithms. So this was initially done for sorting by Alone et al. And then there's been some nice follow-up work by Clarkson, Seshadri, and others on low-dimensional convex geometry. So let me explain to you what they were doing. So the PAC formalism is pretty implicit in this literature, but let me explain to you what they're doing when they do self-improving sorting algorithms, and I think the analogy will be clear. So they had in mind, arrays. So input arrays of length n coming from some distribution. And the only assumption they made was that different array entries were independent. They didn't have to be identically distributed, but they needed them to be independently distributed. So you're getting these arrays of length n drawn from this unknown distribution, and you want to, with ideally as few number of training examples as possible, figure out a sorting algorithm which is almost as good as the information theoretic optimal sorting algorithm for this unknown distribution. Because you want to minimize the expected number of comparisons with respect to this unknown distribution. And they show that this can be done. So they show with a relatively small number of samples, and some suitable data structures, you really can have algorithms which are simultaneously competitive with the optimum for any product distribution over array entries. So that's self-improving algorithms, a lot of nice stuff there. Another thing which I think Anna will probably talk about tomorrow is the idea of sort of taking the PAC mindset and applying it to auction design. So this again is part of algorithmic game theory. So in economics, forever the dominant paradigm has been what we would call average case analysis. They would call it Bayesian analysis, right? So there's like this common prior assumption in most economic work, and then you optimize with respect to the prior. So that's the sense in which it's average case analysis. But if you want to try to apply that theory, for example, to figure out how to set reserve prices in a sponsored search auction or whatever, there's always this question which is like, what is this common prior? Where do I get this distribution from? But of course, for computer scientists, the answer is sort of obvious, right? It should be from data from the past. And boy, does that sound like a learning problem. You're given samples of bids from auctions in the past. You want to use that to get an auction which is almost optimal with respect to an unknown distribution. And indeed, just recently, there's been developing lots of strong and useful connections between auction theory on the one hand and statistical learning theory on the other hand. And then finally, let me just mention, this will be the topic of the open lecture that I'm giving in October. And this is also, sort of directly inspired by some of the work you'll hear from Kevin in the afternoon. So the idea of, in practice, what if you don't want to design an algorithm from scratch? What if rather you have an algorithm portfolio, so a bunch of algorithms for the same problem with widely varying performance, and you want to figure out which one to use? What's the best algorithm for your particular set of instances? Or maybe you want to kind of even take it to the next level and actually, based on coarse features of an instance on the fly, select which algorithm from your portfolio you want to run on it. Okay, so like SAT would be one example where this works great. And so for years I've been sort of inspired by Kevin's results, and I wondered, what would a theory look like that kind of mirrors what he's doing? And this has been the best I've been able to come up with so far. So I'll talk about that more in October. I want to do one more thing, again short. So this is meant to tie together the two parts of the tutorial. Okay, so both tutorials have been about, what are models of data, that sort of deem some inputs more relevant than others. The difference was in part one, we were looking at deterministic conditions, like these stability notions for clustering, the RIP condition for compressed sensing. In part two, we've been looking at all probabilistic models, okay, semi-random models, smooth analysis, and other hybrid models. So the last point I want to make is that actually, these two worlds have a fruitful connection between the two. Specifically, you can think about the probabilistic models we've been talking about in part two and use them to generate, in a basically almost automatic way, novel deterministic conditions, okay, for results of the type we were seeing in part one. I know that sounds a little vague, so I'm just going to do 2 examples, revisiting things you've already seen and interpreting them in a different way. And then I'm just going to mention 2 new things which apply these same paradigm to problems you haven't seen. Okay? So the first thing that I just want to revisit was our L1 minimization recovery result in the compressive sensing setting. So remember this, here we had an underdetermined linear system, and we wanted to use a linear program to get back an unknown sparse signal. And one way you can think about what we did, so remember we knew we needed conditions on A, because it's an NP-hard problem in general. One way to think about what we did here is, well, imagine we first did just sort of an average case thought experiment. We said, well, what if the constraint matrix was random? I'm not saying it's random, but just for fun, as the analyst, imagine it was random, say like Gaussians. Then you could imagine proving that with high probability, L1 minimization works. And then from your proof, you can then back out what it was about a random matrix you actually needed to get the recovery guarantee. So that's one way you could kind of motivate like where an RIP condition comes from. You say, what is really the property of a random matrix which drives this result? Okay? So you do an average case thought experiment with a random matrix, but then from it you extract a deterministic condition, a deterministic restriction on the input, which has the guarantee. And this, of course, is stronger. Right? So if you pick a random matrix, it'll satisfy this with high probability, but there'll be other totally non-random matrices which also satisfy this condition, like say the Fourier matrix, and then you also get polynomial time recovery. So it's always sort of better to have a deterministic surrogate if you can get away with it. So that's the first example I wanted to revisit. The second example is one you saw Nicola talk about at length and with great eloquence yesterday, the idea of online learning, okay, and minimizing regret. So let me remind you the setting from yesterday. So there's some action set. Maybe you want to buy or sell a stock, and you have some time horizon of capital T days. And it's this very unfair feeling game where you or your algorithm has to first commit to an action, or distribution over actions if you like, and then the adversary gets to go second and sort of give you whatever reward vector it wants. Okay? Which sounds very unfair, and it is in a way. And so what's easy to prove is that there's, if you try to apply competitive analysis in the most straightforward way, it's again one of these epic fails. Okay? It says all algorithms are equally terrible, it doesn't lead you to design anything interesting. So the obvious way to do competitive analysis would be to try to compete with the best action sequence in hindsight. Okay? If you could go back in time and choose the best action every possible day, how much better would you have done? Okay? And compared to this benchmark, every algorithm is terrible. But, and this is kind of amazing, if you change the benchmark, okay, if you say, I don't want to compete with the best action sequence in hindsight, I just want to compete with the best fixed action in hindsight, everything changes. Okay? All of a sudden, we have this really beautiful and deep theory, basically just because we changed the benchmark. With the obvious benchmark, there were no interesting algorithms. With this benchmark, we're naturally led to really cool algorithms like you saw yesterday, hedge, multiplicative weights, whatever you want to call it. So somehow getting the benchmark right was fundamental to getting sort of this theory off of the ground. So that's cool, but there's sort of this question, there's sort of a twofold question. So first of all, still, what exactly does it mean? So it's cool we can do it, but what does it mean to compete with the best fixed action in hindsight when our algorithm is not actually using a fixed action, right? So it seems kind of apples and oranges, how to interpret that. But maybe more importantly, like suppose you wanted to find the right benchmark in some other problem, what lesson could you extract from no regret online learning that might generalize to some other domain you might want to think about? So let me again propose a sort of average case thought experiment. And it's just a reinterpretation of this well-known stuff. So imagine I told you that there's some distribution D on reward vectors, and every day the reward vector is going to be chosen, IID, from this distribution D. So this is a trivial problem for online learning, right? So what are you going to do on day one? We're going to say, well, which action has the best reward, the highest expected reward? I'm going to play that. What are you going to do on day two? Well, the same thing, because it's again another IID draw from the same distribution. So if you knew a distribution and you knew that reward vectors were being drawn from them, you would just play the same optimal action every single time step. You would use a fixed action if you knew that it was IID from a distribution D. Suppose you didn't know D, but you knew the reward vectors were IID. Well, you don't know D, so you don't know the best fixed action, but you know there's some fixed action which is optimal. So what would be an interpretation of doing the best fixed action in hindsight? Well, it's certainly an only stronger statement than saying you're competing with the actual optimum, right? So the real best action sequence in hindsight for every unknown distribution D, under the assumption that the reward vectors are IID. Okay? And if you think about it, actually from this thought experiment, you can just generate this benchmark of the best fixed action in hindsight. You can go to the average case thought experiment, say as I range over all unknown distributions D, what are all of the different optimal strategies that arise? Well, that's just all of the optimal fixed actions. And this now induces a deterministic criterion, a deterministic benchmark, the best fixed action in hindsight. It's the best optimal strategy that it might have been had it been an IID distribution. Now, just in the compressed sensing world, it's better to have the worst case guarantees than to have this, right? So in the worst case guarantees, you're going to get no regret, even when the reward vectors are adversarial and not stochastic. So you get a meaningful guarantee more generally, but in particular, it holds in this case. And again, sort of the takeaway point is that this thought experiment naturally leads you to discover that best fixed action benchmark. Another kind of folklore example you might want to think about would be when you talk about, say, static optimality for search trees. That's really just saying you're competing with the best search tree on any sequence of IID accesses. Exactly the same kind of thing. All right, so last slide. I revisited two things. Kamesh.
Another classic example is this dynamic Huffman coding. I think that was the first context in which this was.
Sure. Yep, that's a good example. And there you're actually just, there you're just optimal, basically. Yeah. Yep.
So in the distributions that you had before, does it matter if they're heavy-tailed or light-tailed? Are you making some assumptions about them when you're looking at the range of all distributions?
Good question. Depends on the problem. I mean, in general, so when you're doing these hybrid models, right? So deciding on a hybrid model amounts to deciding on a class of distributions. And you basically can never get away with all distributions, because that would include all possible point masses, which would get you back to worst case analysis. So you need to sort of assume, something. So like in the self-improving algorithms work that I mentioned, they assumed independence between the array entries. So they didn't assume they're identically distributed, but they needed to be a product distribution. In the algorithmic game theory results, usually, again, you need to assume a product distribution. And then in that context, if you have, you either need some kind of bound on the range of values, or you need some control on the tail of the distributions. So the right way to define those distributions is going to be problem specific. But I just think this is a good mindset to have. Okay, so last slide. So the two things I just revisited accomplished two different things. Both had in common that we thought about the average case world, not because we were literally going to analyze the average case world, but more because we were confused about what should we be studying in the deterministic world. In the compressed sensing case, we did the average case thought experiment, not to suggest a benchmark, that's not what we were doing, but to suggest a deterministic condition on inputs. Basically to have a novel way to identify a special case of an NP-hard problem. Okay, that's what it accomplished in compressed sensing. What it accomplished in online learning was it generated this benchmark. Okay, it gave us this best fixed action in hindsight instead of the perhaps more obvious best fixed action sequence in hindsight. So do these things have, does this paradigm have other uses? It does. So one thing which I'm not sure whether or not Anna will talk about tomorrow, but another part of algorithmic game theory where the whole point in getting the theory up and running was to find the right benchmarks was prior free auction design. So this was pioneered by Goldberg, Hartline, Carlin, Sachs, and Wright. Their motivation was having a worst case analog of the traditional economic theory, which is average case analysis of auctions. And again, just like with online learning, if you take the obvious approach of competitive analysis, it tells you all auctions suck, and they all suck equally. So you just get nothing. You do not have an interesting theory. But Goldberg et al. Proposed benchmarks analogous to the best fixed action in hindsight, such that it does naturally guide you to designing really interesting auctions with worst case guarantees for that benchmark. And then in work with Jason Hartline, we use this same kind of average case thought experiment to generalize and sort of maybe make more automatic this goal of proposing relevant revenue benchmarks. So basically, you do an average case thought experiment. You say, well, assume bidders actually are coming from a distribution. I don't know what the distribution is, but I'll at least assume that they're independent. What are all of the different optimal things I might want to do? Ranging over all distributions for IID bidders. And then I want to compete with the best of all of those optimal things I might want to do in the IID case. Exactly analogous in no-regret online learning, where the best fixed action can be interpreted as the range of all the best things you might want to do in the IID case. Same thing works here. So back to defining deterministic conditions, so analogous to compressive sensing. This is what I'll talk about in the workshop in September, which is applying that sort of philosophy to social networks. Typically in the study of social and information networks, people study them with generative models, right? You might have heard of like preferential attachment or the Chung-Lu model, these kinds of things. And so the question is, okay, can you take a hybrid model approach? Can you say, well, wouldn't it be cool to have an algorithm which worked kind of no matter which generative model you believed in? So here the class of distributions are going to be all plausive generative models for social networks. And we use that distribution in this thought experiment to get deterministic conditions on graphs. So if you like, just graph classes. We identify graph classes meant to capture all plausible social networks. So we focus on properties related to triadic closure. Okay, so that's how you do this here. There's also been some follow-up work, including here at Berkeley. Okay. So that wraps up what I want to say. I'll leave the part 2 summary up on the slide and happy to take more questions. Thanks a lot.
Everybody wants to answer?
Yep.